Okay, so welcome to IITN Gate classes. Today we'll be discussing on Jet Propulsion Gate Aerospace 2014 paper. So the questions from Jet Propulsion part we'll be solving here. So myself Akshay. So in 2014, there were like 4 1-mark questions and 4 2-mark questions were asked, and the totals about 12 marks from the core jet propulsion. So let us jump on to the problem. The first question is, match the appropriate engine in the right column with the corresponding aircraft in the left column for most efficient performance of the engine. So in the left column, I have 4 different types of aircrafts. Like one is low speed transport aircraft, high speed subsonic civilian aircraft, supersonic fighter aircraft, and hypersonic aircraft. Whereas in the right column, I have 4 different engines. So say like one is Ramjet, turboprop, turbojet, and turbofan. So they are asking us to match which suits better for the given application. So for the low speed transport aircraft, so usually Mach number is less than zero point 0.5 or so. So for that, a turboprop is more useful. And for the high subsonic aircraft, so say Mach number greater than 0 0.5, so for that, like you generally prefer turbofan engines. For supersonic fighter aircrafts, the most reliable engine is turbojet, and hypersonic and high supersonic and hypersonic, so that is going to be Ramjet engine. So based on this comparison, A goes to 2, B goes to 4, C goes to 3, and D goes to 1. So that is option D. So for this, option D is uh, more appropriate answer. Okay, so moving on to the next question. For a given fuel flow rate and thermal efficiency, the takeoff thrust for a gas turbine engine burning aviation turbine fuel is very tricky question, and there is no direct way to answer this question, because you see the performance of a turbojet engine we usually do for a cruise condition or a design altitude condition, and this is a exemplary case where they are asking during the takeoff. So during the takeoff, you have to generalize this problem in the other direction. You have to look from a different point of view. During the takeoff, what actually happens? You are accelerating the flight, right? So when you are accelerating the flight, what does it means? So I have a thrust equation. Say for optimum condition, I really don't worry about the pressure thrust for this part. So that is nothing but mass flow rate of gas times Cj minus mass flow rate of air times Ci, right? And they asked you to consider fuel to air ratio to be very very small. So this can be written as mass flow rate of air times 1 plus F times Cj minus mass flow rate of air times Ci. So if I take mass flow rate of air common and considering F to be very very small, so neglecting this part, so this comes out to be Cj minus Ci. So if you look at your thrust equation, your your obvious choice would be increases with Cj, because the 4 options they are given, the thrust is directly proportional to exhaust velocity, inversely proportional to exhaust velocity, independent of exhaust velocity, directly proportional to the square of the exhaust velocity. So your obvious choice goes towards saying it increases with exhaust velocity, but that is wrong. Why? Because the purpose here is we are accelerating the flight, so we cannot neglect the Ci part, right? The incoming air velocity, that is very very important. That induces momentum drag. So that is a part of thrust which goes in a negative direction. That means that is going to cancel out your useful thrust here. So that is why if I rearrange this particular equation, taking Cj common, it becomes 1 minus Ci by Cj. So now you see, if I Ci increases during the takeoff phase, that means this particular quantity is going to increase. That means 1 minus that is going to decrease. So thrust is kind of decreases with increase in Cj. So this is an indirect way to answer this question because there is no direct way. And the relative increase in exhaust velocity is much lower compared to the relative increase in forward speed, the acceleration speed, because it is not a cruise condition. Remember, it's a takeoff condition where you are increasing the Ci, flight speed. So the relative increase in Ci is much greater in percentage compared to the relative increase in Cj. So that is why, so the increase in Cj will result in decrease in thrust. So this is kind of inversely proportional to the exhaust velocity. So this very interesting question. So let us move on to the next one. For a 50% reaction axial compressor state, following statements are given. Velocity triangles at the entry and exit of the rotor are symmetrical. The second statement says that the whirl or swirl component of absolute velocity at the entry of the rotor and entry of the stator are same. Which of the following options are correct? This is again a straightforward question. So let us try to draw this stage velocity triangle. So I have a rotor, so C1 absolute velocity vector, W1 relative velocity vector, Ca is axial component of velocity, and U is blade velocity, right? So at the exit of the triangle again, so I have exit velocity triangle with Ca, C2, W2 and U. Here we are making a few of the assumption, that is we are analyzing at a given mean blade speed or mean given height, and axial velocity doesn't change as it passes through a stage. So those assumption we are making here. So that makes our analysis much more simpler. Alpha 2, beta 2. So now if I look at the degree of reaction equation, that says me 5 by 2 tan beta 1 minus tan beta 2 kind of way. So if R is equal to 1 by 2, that gives me beta 1, sorry, not this equation. So let us try to use with the other form, that is 1 by 2 plus 5 by 2 times tan beta 1 minus tan alpha 2 form. That's the other form of degree of reaction. So from here we can easily show that beta 1 is equal to alpha 2. Similarly, we can also show that alpha 1 is equal to beta 2. So two angles are similar and one of the velocity component U is similar. So that makes our triangle to be symmetrical. So that is why the first statement is already true, but the second statement, that is very interesting. What they are saying, swirl or the whirl component of absolute velocity, that is nothing but this component Ct. This is at the rotor entry, and at the rotor exit, that is nothing but the stator entry, the next stage stator, right? So CT2. And we know for a reason, if I want to expect a work done by the compressor on the fluid, that means our Euler energy equation that says me U times CT2 minus CT1. If those two are same, then I am expecting no energy transfer at all. That means this compressor is useless. But 50% reaction by definition itself says there is a 50% work is being done by the rotor stage. So that is why there is a work transfer that we already know. So that means these two components cannot be same. They are different. So the second statement is wrong. So based on this statement, which options is correct now? Option B, right? The statement 1 is correct, but the second is incorrect. Right? Yes. So let us move on to the next one. The thrust produced by the turbojet engine. Option A increases with increase in compressor pressure ratio. Option B decreases with increase in compressor pressure ratio. Option C remains constant with the increase in compressor pressure ratio. Option D first increases then decreases with increase in compressor pressure ratio. This one we actually discussed during our class. So this is much of an optimization problem. So few of the things we are going to assume, that is we are going to see for this particular question for a given flight Mach number and at a given altitude. So that we are going to fix to answer this question. Now you see this graph, how the thrust is varying with the increase in compressor pressure ratio. It increases to a certain compressor pressure ratio and then it decreases, right? So if I keep on increase the compressor pressure ratio, it is not going to increase the thrust. So though it's a specific thrust, but we can extrapolate this idea to thrust also. So this kind of gives you an idea that first it increases and then it decreases with increase in pressure ratio, right? So these maps are very handy for the gate point of view. So this helps you answer some of the questions which is being asked in previous year gate. Okay. So yes, anybody is having any question? Yes, I told you once, the idea can be extrapolated over here, though they are asking the specific thrust. What is specific thrust? It is thrust per unit mass flow rate of air. And my assumption here is like I am not changing the mass flow rate which is coming into the engine. So from that, like we have to make certain assumption to answer this kind of questions, because it is not purely quantitative analysis, it's a qualitative one. Certain assumption we have to invoke, but I am not making other assumptions such that like SFC is constant, a turbine inlet temperature is constant. Those assumptions I am not making, because that is very difficult to make out that assumptions. Okay, the few of the assumptions I am making here is like Mach number is same and altitude is same and the mass flow rate which is coming into the engine, that is same. Other than that, I am not making any other assumption. Okay. Okay. Now let us move on to the 2 marks questions. A cruise missile with an ideal ramjet engine is flying at Mach number 4 at an altitude where the ambient temperature is 100 Kelvin. Consider a ratio of specific heats, gamma is 1.4 and specific gas constant R is equal to 287 joules per kg Kelvin. If the stagnation temperature in the combustion chamber is equal to 2310 Kelvin, the speed of the exhaust gases is. It's a kind of a repetitive question. So we saw similar kind of question in the 2020 gate also. So it's a very similar question here. Okay. Vasant, your question is from the previous question, right? Your doubt is from the previous question. If they're asking overall thrust means it's same. What do you exactly mean by overall thrust? Okay, if it's clear, it's fine. Okay, so coming back to this question, it's a repeated question, kind of. So let us try to draw the control volume. I have a Ramjet engine. So I have a converging diverging nozzle, right? So now it expands the fluid at T03 and P03 to exit pressure PE and exit plane temperature is TE, right? So they are also given the ambient temperature, that is TA, equal to 100 Kelvin. Note that TE is not equal to TA, but PE can be assumed to be PA given that it's optimally expanded. That's the assumption we are going to make here. And I have exit Mach number ME and incoming Mach number MI. So we know that ideal ramjet, that means Mi is equal to Me. So incoming Mach number and exit Mach numbers are same. Other things they are specified here is gamma as 1.4 and R is equal to 287 joules per kg Kelvin. So this is the condition they are given, and T03 is specified to you, that is 2310 Kelvin. So these are the conditions we have at hand. All they are asking is what is the exhaust jet velocity, that is what is CJ. So from the ideal ramjet condition, Mi is equal to Me, that is nothing but Ci divided by root of gamma R Ta should be equal to Cj divided by root of gamma G Rg times Te. And if I want to calculate Cj, I can calculate like that, Me times root of gamma G Rg Te. So this is the straightforward way. And only unknown we have here is Te. So now how we can calculate Te? So to calculate Te, I can use the isentropic relation, that is assuming even adiabatic relation works here for temp energy equation. T naught by Te is equal to 1 plus gamma minus 1 by 2 times Me square. Right? So gamma is given to you. Mach number you know from the ideal ramjet condition. So you can calculate what is Te. So you can calculate Te is equal to T naught divided by 1 plus gamma minus 1 by 2 times Me square. Okay. So from here, you actually get T naught by Te to be equal to something around 4.2. So use T naught is 2310 Kelvin, get the Te value. So you substitute back over here. Gamma is given 1.4, R is given 287. So you should able to get Cj as something around 1880.383 meter per second. So let us just put the question. Yeah, they are not specified anything regarding decimal places and all. Let us put the value we got, 1880.383. So remember here, so this question, for this question, they are given the range just 1880 to 1881. So you see, that's like very short range. So you should be able to get 1880 point something. So that's the range they are given. So you cannot off by too much. Okay. So now we will move to the next question. Gas turbine engine is operating under the following conditions. Stagnation temperature at the turbine inlet is 1350 Kelvin. Stagnation pressure at the turbine inlet is the 10 bar. Static temperature at the turbine exit is 800 Kelvin. Velocity at the turbine exit is 200 meter per second. Total to total efficiency of the turbine is 0.96. Gamma is 1.33. Cp is 1147 joules per kg Kelvin. The stagnation pressure in bar in the nozzle, considering the isentropic nozzle, is equal to. It's a very straightforward question, but they are asked in an indirect way. So let us try to draw the control volume for the given condition. So I have a turbo jet engine kind of thing. So I have a compressor following a combustion chamber, then it is connected to turbine, and then I have a propelling nozzle from here to here. So all they are given is the turbine entry condition. Say it is station 1, station 2, station 3, and station 4. Let it call it as station 5. So now you see, they told assume isentropic nozzle. So if I want to assume it's an isentropic nozzle, that means the flow inside the nozzle is isentropic. So that means P04 is equal to P05. So my P0 is constant for an isentropic flow, assuming it's a steady case. So now all I have to calculate is what is P04. If I calculate P04, that is the stagnation pressure inside the nozzle. So to calculate P04, they are given the turbine inlet condition. T03 is given to you, P03 is given to you, and T04 is given to you, and efficiency of the turbine is given to you. So from here you can actually calculate P04, right? So if I draw the TS diagram for the expansion process in the turbine, so that is actually expanding from P03 to P04, total to total. So now it is at some temperature T03. From here it is expanding to T04. This is an actual curve. This is S is equal to constant line. This is going to be hypothetical point where it meets the S is equal to constant line. So if I use the turbine efficiency idea, so I can write it to be equal to T03 minus T04 divided by T03 minus T04 dash. And if I take T03 common from the denominator, it makes it to be T03 minus T04 divided by T03 1 minus T04 dash divided by T03. Now you see T04 dash and T03 both lies on the constant entropy line. So the as a state wise, S2 minus S1 is going to be 0 for this case. So I can use the isentropic relation between these two states. So that actually relates to actual pressure, right? So I can write it to be T03 minus T04 divided by T03 times 1 minus T04 dash by T03 can be written as P04 by P03 to the power of gamma minus 1 by gamma. So now all I have to calculate is P04. So let us rewrite this equation in terms of that ratio. So I have eta T times T03 is equal to T03 minus T04 divided by 1 minus P04 divided by P03 to the power of gamma minus 1 by gamma. And if I take that to the other side, gamma, which is equal to T naught 3 minus T naught 4 divided by eta turbine times T naught 3, and write it for this one. So P naught 4 by P naught 3 to the power of gamma minus 1 by gamma equal to 1 minus T naught 3 minus T naught 4 divided by times T naught 3. So now raise the other side, that exponent. So that is going to be P naught 3 times 1 minus T naught 3 minus T naught 4 divided by eta T times T naught 3 to the power of gamma by gamma minus 1. So now everything is known to you. Put the numbers. P naught 3 is 10 bar, T naught 3 and T naught 4 is given 1350, and what's the T naught 4 they are given, that is T naught 4 is not given directly, so we have to calculate because static temperature is given as 800 Kelvin and velocity is given, so that is 200 meter per second. So from here I can calculate T naught 4 using energy equation. So that is nothing but T4 plus V4 square divided by 2 Cp, and Cp is given to you 1147. You use that one, you should be able to get T naught 4 as 817.44 Kelvin. So use this value of T naught 4 over here, and 96% as turbine efficiency. Should be able to get P naught 4 as 1.185 bar. So that is, we'll put here 1.185 in bar. Yes. Clear, right? It's a straightforward question. Yes. So now let us move on to the next question. Air at stagnation temperature of 3000 Kelvin and the properties of air is given as specific ratio of specific heat gamma as 1.4 and specific gas constant R as 287 joules per kg Kelvin. Enters the impeller of a centrifugal compressor in axial direction. Stagnation pressure ratio between the diffuser outlet and the impeller inlet is 4.0. The impeller blade radius is 0.3 meter and it is rotating at 15,000 revolution per minute. If the slip factor, that is ratio of the tangential component of air velocity to the blade tip velocity to the blade tip at the blade tip is 0.88, the overall efficiency of the compressor is. Again, a straightforward question. So let us try to draw the information in control volume manner. So I have a centrifugal compressor. Okay. Okay. So this is my axis of rotation. I am just drawing one half of the centrifugal compressor. So I have an inlet, then the flow goes like this and leaves radially, right? So it comes axially and goes radially. So the moment when they say it enters axially, that means my absolute velocity C1 is also equal to CA. That implies that CT1, that's the tangential component at the entry, is going to be 0 because I don't have any swirl component associated with that one in the tangential direction, right? So my Euler energy equation says that the work transfer or the energy transfer from the rotating machine to the fluid is going to be U2 CT2 minus U1 CT1. So if CT1 is 0, this part goes to 0. So that just leaves me it as U2 CT2. So now this part is clear. This part is clear. So now why we need this one? Because our ultimate goal is to calculate the efficiency of the compressor. So what is efficiency of the compressor? That can be shown as T02 dash minus T01 divided by T02 minus T01. So here this can be written as T01 times T02 dash by T01. That can be written as the pressure ratio in the compressor to the power of gamma minus 1 by gamma minus 1 divided by T02 minus T01. That is nothing but delta T0 change in the compressor. So this one we have to calculate because other things are known to us, but delta T naught is not known. So to calculate that one, I need this information. Why? Because from applying first law of thermodynamics to the steady flow, so I can write this to be equal to Cp times delta T naught in the compressor equal to U2CT2. So I can easily calculate this one equal to U2CT2 divided by Cp. So now, what are the unknowns over here? First, we don't know what is U2. So to calculate U2, it is nothing but angular speed times the radial, position vector. So that can be written in terms of pi dn divided by 60, right? So this can easily written as pi dn divided by 60, and U2CT2, if slip factor is given to us, what do we mean by a slip factor? If I draw the exit velocity triangle, my U2, CR, C2, and this is relative velocity at the exit. So this is CT2. So the slip factor is nothing but the ratio of actual tangential velocity to the ideal tangential velocity, that is for a radial vane impellers, that is CT2 by U2. So I can write CT2 to be equal to sigma times U2. So I can easily replace delta T naught equation with sigma times U2 square divided by Cp. So now U2 is pi dn by 60. So I am just replacing that one, pi dn divided by 60 whole square divided by Cp. So now you calculate this one, you should be able to get delta T naught from this one. So if you put this back into the efficiency formula, so that is nothing but eta C is T naught 1 times pi c to the power of gamma minus 1 by gamma minus 1 divided by delta T naught. So you keep all the values what you got. So you should be able to get efficiency to be equal to 0.7494. So in percentage wise, it is going to be something around 74.94 or nearly equal to 75%. You can either keep 74.94 as your answer, or you can keep 75. It's fine. So clear, right? This question? Yes. Okay. An aircraft is flying at Mach 3 at an altitude where the ambient pressure and the temperature are 50 kilopascal and 200 Kelvin respectively. If the converging diverging diffuser of the engine, considered isentropic with ratio of specific heats is gamma 1.4 and specific gas constant R as 287 joules per kg Kelvin, has a throat area of 0.05 meter square, the mass flow rate through the engine is more of a gas dynamics question since it is asked as a intake. So I'm just taking this question over here. Sorry. So again, I'm going to draw the control volume for this one, considering converging diverging diffuser. So this is my entry section where incoming flow has Mach number mi as 3 and the ambient conditions are Ta is 200 Kelvin and pressure is 50 kilopascal. Okay, what else is given? The throat area is given, area at the throat. So that is 0.05 meter square. Okay, so they are asking you to calculate the mass flow rate through the engine. And look at the question very carefully. If the incoming velocity is supersonic and you want it to be slowed down to subsonic values, so that means somewhere within the duct we have to encounter a sonic condition, and usually the mathematics will guides us the minimum area of the duct where we can expect a sonic condition. So that means at the throat we are going to experience the choked condition. That means there the Mach number at the throat becomes 1. Okay, so that's the gas dynamics will tells us. So for that one, what we can do is I can easily relate it to be mass flow rate is constant from the continuity. So like rho 1 A1 V1 should be equal to rho star A star V star. A star is throat area, rho star is density at the throat, and V star is the velocity at the throat. And if Mach number becomes 1 at the throat, that means V star is also equal to speed of sound at the throat. So I can write it as to be gamma R T star. So if I replace that one and rho star, what I am doing, I am multiplying and dividing by rho naught. So and rho naught I am writing in terms of P naught by R T naught because equation of state can be used at any state. So P is equal to rho RT, assuming it's calorically perfect gas, which is moving through the duct. So again, A star remains A star. V star is nothing but root of gamma R. Again, T star I am writing in terms of T star divided by T naught multiplied with T naught. So now you see, so this becomes rho star by rho naught. So if rho star by rho naught, I can use the isentropic relation. That is nothing but rho naught by rho is nothing but 1 plus gamma minus 1 by 2 times m square to the power of 1 by gamma minus 1 kind of idea. So if I use that one and put m is equal to 1 for at the throat condition, so this comes out to be something around 2 by gamma plus 1 to the power of 1 by gamma plus gamma minus 1, and P naught divided by root of RT naught. So here I am taking RT naught common. So this becomes RT naught to the root gamma times again T star by T naught can be written again in terms of 2 by gamma plus 1. So that is going to be 2 by gamma plus 1 to the power of 1 by 2 times A star, right? So now my equation is simplified. So 2 by gamma plus 1, 2 by gamma plus 1. If I take LCM of these powers, so it becomes 2 by gamma plus 1 to the power of gamma plus 1 divided by 2 times gamma minus 1 times P naught divided by root RT naught times root of gamma times A star. So now everything is known to us. A star is 0.05 meter square. P naught we can easily calculate because P is given in the problem. So I can use the isentropic relation at the inlet. P naught by PA is equal to 1 plus gamma minus 1 by 2 times Mi square to the power of gamma by gamma minus 1. From here I can calculate P naught. Similarly, T naught also I can calculate. T naught by TA is equal to 1 plus gamma minus 1 by 2 times Mi square. So from here I can calculate T naught. So if you calculate all the values, you should be able to get P naught is something around 1836.64 kilopascal and T naught is something around
ಅದು ಇವಾಗ ಇದರಲ್ಲಿ ಬಿಗ್ ಡೇಟಾದಲ್ಲೆಲ್ಲ ಏನು ಅಂದ್ರೆ
560 Kelvin. So now if I use those values over here, I should be able to get mass flow rate to be equal to something around 157 kgs per second. It comes around 156.9. So but there are 4 options given in the question. So out of which 157 is very close. So I can choose option D as my answer. So clear? Yes. I think that was our last question from the GATE 2014. So thank you for attending the session. If you guys have any question, you can ask now. Okay, the second question, that is the takeoff condition, right? The question which asked about takeoff condition. Okay, so like that is one exception. Okay, so like usually in the GATE I never seen a question which is coming out of the thinking ideas. Like usually they ask from a for a cruise condition, because for that condition only we do all the analysis. Okay, landing and other things, right? So you have to think from a perspective of that one. So what you are actually doing, right? So there it's kind of an opposite, right? There you are decelerating the flow. So decelerating the flight. So if you are decelerating the flight, that means CJ also decelerating as well as CI also decelerating. That means it increases the thrust to a certain extent, right? So you have to think on the viewpoint, what you are actually trying to do. It's not only depends on that factor alone. Okay, for the discussion of that problem, I just brought in the idea of increase in CI, but there is a density which comes into picture that changes the mass flow rate, because you are also changing the altitude during the takeoff. That is a very, very crucial factor. Not just the flight speed is the sole variable. There are other variables which are important. Mach number and flight speeds are very, very different. Mach number is defined with respect to flight speed and the ambient temperature. That ambient temperature is also changing because during the takeoff you are changing the altitude. So there are so many other part which comes into picture we did not see, but depending on the question you have to think. Okay. Anything else? What is the difference between the ideal characteristic velocity and characteristic? Okay, it's going out of our discussion over here, but still I can bring in the discussion. It's a characteristic velocity. That means like you are referring to the rocket propulsion part where we use or define C star to be equal to P naught AT divided by M dot, right? So now you see here, it really out of a syllabus part, at least for gate aero. Okay, ideal and actual characteristic velocities. You have to understand the idea of characteristic velocity. What exactly the characteristic velocity says us? It is one of the parameters which makes your comparison between different propulsion system of the rocket independent of the type of the propellant you are using. So the thing is, here we are only worried about what is the stagnation condition at the chamber, what is the throat area, and what is the mass flow rate. Nothing else. We are not really worried about what is the density of the fuel you are using or what is the nozzle we are going to use, because area of the throat doesn't define the nozzle. It's just one part of the nozzle. If you want to fix the geometry, then you have to fix the area ratio. That is not there. P naught, again, this is the stagnation chamber pressure. It doesn't really care about whether you are achieving the stagnation chamber pressure through a solid propellant or the liquid propellant. So it's a very important parameter, a key parameter, which can be useful in comparing different propulsion unit, irrespective of the type of the propellant you are using. So that's the idea of characteristic velocity. The definition of characteristic velocity we define in this way. If you understood that part, that's more than sufficient. Don't worry about which is beyond your thinking. Okay, it's which is beyond your syllabus. Those are the advanced rocket propulsion ideas, the ideal and actual conditions, and all, comparing those things and mapping out those things with respect to different variables such as so we also have thrust coefficients, so mapping out with C star and CF with respect to ideal and actual conditions. All these things are beyond your gate syllabus. Your focus should be on what you actually have in the hand. Mock test, you might have seen this question, I can agree, but don't worry. All mock test questions are not exactly designed with respect to the um, gate syllabus. There are some questions, at least some questions which are advanced than the gate level. That is just to make sure that you you don't get panicked during the exam. There are certain questions which comes in actual gate also, which will be like very different from what you have studied so far, and those are the questions you should be very wise in deciding. It might look familiar, but you have to think whether you know how to approach this question or not, because those are the questions you can easily get stuck for a 10-15 minutes. At the end you will come to a conclusion that I cannot solve. But what exactly you did there? You lost a very valuable 12 to 13 minutes where you could have solved a different questions. That is the time where you come to a panic mode, because number of questions are more and the time remaining is less. That is the place where you try to make mistakes. So you have to avoid those questions very carefully. So that is why, like, even in IGC mock test, you will see certain questions which are really looks familiar, but you cannot solve because you are not actually studied those advanced topics to solve that questions. So those are the questions you have to make a wise choice, whether you know how to proceed for this one or not. Okay. So there will be certain questions. It is just to make sure you will be having some tough times during the exams. Okay. Don't worry about all the questions, um, whether you can solve it or not. Gate is not about solving all 100 marks. It is about solving relatively higher marks than the your other test takers, compared to other test takers. Whether you are able to make most of them solved or not. Not all of them. You have to understand it's a relative system. Okay, it's very very important. Okay. Okay then. So if you guys have no other questions, we can wind up this session over here. See you guys.